Hello everyone. In continuity of our lecture series on broadening of spectral lines, we have done the basic introduction of broadening mechanism, homogeneous and inhomogeneous broadening mechanisms. Then we also studied that the example of homogeneous broadening mechanism are natural broadening and collision broadening, whereas the example of inhomogeneous broadening is Doppler broadening. In the previous lecture, we discussed natural broadening. What's the reason behind that? The main explanation behind natural broadening is Heisenberg's uncertainty principle. Today, we are going to derive for natural broadening or intrinsic broadening that we also say. We are going to find what amount of broadening would be there, what stretch would be there in the line if there is some natural frequency omega naught, then how much extra or how much deviation can we expect in case of natural broadening. As I told earlier that the central frequency we often talk of is the one where maximum photons are emitted having that frequency, which gives us a peak, a very huge peak and a very long central line. That corresponds to central frequency because we obtain maximum number of photons relating to that frequency. We often denote it by nu naught, but here now we are going to understand the same concept in terms of electrical oscillator. It's not that we are talking of any electrical circuit. No, the levels that we say that atom jump from one level to another, it jumps from lower energy level to higher energy level if it absorbs radiation, and when it is on higher energy level, the moment the lifetime of that state terminates or is over, it jumps back to lower energy state. So that jumping continues. There is a continuous jumping between the two levels. Sometimes atom is jumping here and sometimes atom is coming back down. There is continuous jumping. Due to this, we call this whole system as an electrical oscillator. So we can relate it as an electrical oscillator for an emission of radiation. So the equation of that electrical oscillator for emission of radiation is given by E double dot plus gamma E dot plus omega naught square E is equal to 0, where E is the electric field. This is the electric field. This means d square E by dt square. This means dE by dt. And this is our damping factor. Now, why this damping factor is there? When the emission of radiations continue, we say that this process of jumping of atoms from one level to another just keeps on happening. So we will be getting different radiations emitted. We will be obtaining different radiations, different photons of different frequencies. Whenever there is emission of radiation, there is dissipation of energy as well. Dissipation losses are always there. Even if we talk of atoms in such microscopic scale, even then some sort of dissipation is always there. Damping is simply what? When we say that we give any oscillation, if we have a pendulum attached with a string to some support, there is a bob and we just give a swing to that bob, what will happen? That it would start with its maximum amplitude, it will start vibrating and it will go to some extreme position and come back. This thing would get repeated like this would get repeated, but then after what will happen? With time, as we see, this would decrease. The amplitude of vibration or oscillation would decrease. We will give it to the maximum one. We will start by giving maximum amplitude, maximum swing to the bob, and it will continue displaying those higher amplitudes or going or covering those extreme positions for like 2-3 times, but then afterward the amplitude of oscillation would decrease and decrease, and it will keep on decreasing with time, and finally your pendulum will stop oscillating. So what is happening? We gave the force. Now that energy is being spent every time the pendulum is moving, that some sort of energy is always getting spent, and due to that dissipation of energy, there is no more energy left at some particular time, and it will stop moving, because for motion we need some energy, and if there is no energy left in the pendulum itself, it will not move. So with time it keeps on losing some of its energy. This is damping. Similarly, here in case of lasers, or just when we talk of spontaneous emission, because here I'm particularly referring to spontaneous emissions, because that is the moment where we don't know when the atom would make jump to another level. So in that case also, radiations are getting emitted, which would result in some sort of dissipation of energy, and that's why we include this damping factor. Omega naught, this is the natural angular frequency. As we talk of central frequency nu naught, pertaining to that, or if we would say that corresponding to that central frequency nu naught, we have this natural angular frequency omega. Angular frequency and linear frequency related by this expression. So instead of simple linear frequency, we can mention angular frequency. That's why we are using omega here, because 2 pi is simply a constant, 2 into pi. So here we are talking of angular frequency now, not only central frequency, because we say that photons or radiations are emitted in all directions. So they would cover all the direction, they would cover all the angles. That's why we are taking into account angular frequency and not simple linear frequency. Now the electric field associated with oscillator, if we have to mention that, considering that damping factor is very small, that would be E of t electric field, which is a function of time, because everything is changing with time. Always remember that natural broadening is due to finite lifetime of excited state. So time is really important here. So this is equal to E naught, which is the amplitude, E minus, because it is exponentially decaying. That's why we are using e raised to the power minus of. Always natural angular frequency we denote by iota, plus gamma by 2 t. It's a function of time, so t will always be there. We always mention any electric field or magnetic field in this form whenever we have to mention it in terms of amplitude and the phase. Here phase tells us that omega naught is the natural angular frequency. Plus we have added damping factor. In this damping factor is small than the natural angular frequency. It's not even comparable, it is small. So that with time, after some time has already spent, then some sort of damping would begin. If damping is comparable or greater than omega naught, then no emission would be there, no radiations would be emitted, because then this factor is dominating. If damping is dominating, it means energy is getting dissipated already. You don't have enough energy to release any photons. So we are considering this to be smaller than omega naught, and that's why we are taking this gamma by 2 here. Now we have to write the frequency spectrum associated with this electric field, which will be given by Fourier transform. Now Fourier transform, how do we have to write down? This is E omega omega naught. As I told that this is natural broadening. It means we will not obtain single line in our spectrum. In fact, there would be some other frequencies involved, which would lead to broadening of the spectral line. So those frequencies are being denoted by omega. So omega stand for those frequencies, and omega naught is the central frequency. Okay, this corresponds to central frequency. Fourier transform is always given by 1 upon 2 pi integral of the quantity. So this is 0 to infinity. Now see, the integral would be almost the same. This is E naught All I have to do is introduce omega. This omega has to be introduced in this term. Rest will be the same. How we can write it? We can write it like this. E naught is already there. Exponent is minus iota omega naught and minus gamma by 2 basically. We have to introduce omega here. What I'm trying to do first, iota omega. This is the term I have introduced because angular frequency is always written along with the iota. And then I'm going to write this term, which is minus iota omega naught. And then comes this damping factor, which is minus gamma by 2. And this is time t. We just have introduced this quantity. And of course, dt would be there as this is integral. So integral is always with respect to something, and here we are integrating with respect to time, the change in time that is happening. Further, I can write it as 1 upon 2 pi as it is, 0 to infinity, E naught. Just we are going to separate damping factor from the frequency factor. So I'm going to write e raised to the power minus gamma by 2 t, because this is minus gamma by 2 and t is getting multiplied, plus, now I'm going to combine both the frequency terms. So iota is common, omega minus omega naught t, and then dt would be there. Next, as E naught is simply the amplitude, I can bring it outside the integral. So now I'm left with e raised to power minus gamma by 2t plus, you can write it here, dt plus e raised to the power iota omega minus omega naught t dt. Let's solve it. If we will solve this, we can solve it separately also, but I would prefer solving it as a complete entity. So I'm going to use minus gamma by 2 plus iota omega minus omega naught, and then t is there. But if I take minus common, then this term should become negative. Then I'm writing gamma, and this becomes negative dt. E naught upon 2 pi. Now this has been solved. What is the integral of e raised to power something? This is e raised to the power something as it is upon this portion, the power. We are left with e raised to power minus gamma by 2 minus iota omega minus omega naught t upon this term as it is, the power as it is, which becomes minus gamma by 2. I'm just removing the brackets, plus iota omega minus omega naught. The limits are 0 to infinity that we have to put. E naught upon 2 pi as it is. Now when we put the limits, see, I have written square brackets here. All the symbols that we use while solving, they have their own importance. Whenever we have the integral form, always remember we have to write with respect to what we are integrating. So this term is very important. Once you are done with integration, but you have to still put the limits, we use these bars. And when we actually substitute the limit, then we use these square brackets. So all the symbols that we use, they have their meaning. All the characters that are being used, they have their own meaning. And you should always remember to use them correctly. Now see, all these limits we have to put in place of t. So one time t would take the value infinity, another time it would take the value 0. Since infinity is the upper limit, this becomes e raised to power minus infinity minus e raised to the power minus of 0. So even if I am writing minus of 0, that means 0 upon denominator as it is. Now what is e raised to power minus infinity? E raised to power minus infinity means 1 upon e raised to power infinity. e raised to power infinity, it means if something is exponentially increasing till infinity, that would be infinity in itself. So this, and 1 upon infinity, if a very large number is in the denominator, then the whole quantity itself would become very small. So we mostly write it as 0. E raised to power 0 is 1. So e raised to power minus 0 would also be 1. So back to our derivation, we can write e naught upon 2 pi, e raised to power minus infinity is 0, minus e raised to power 0 is 1 upon minus gamma by 2 plus iota omega minus omega naught. This is the term that we have. This is minus 1 in the numerator. We can cancel this out as, okay, so I'm writing here. This becomes e omega omega naught is equal to e naught upon 2 pi into 1 upon, if we take negative sign common, this would get cancelled here. So we are left with gamma by 2 minus iota omega minus omega naught. This is the thing we have obtained. So just see how we started. Electric field term we wrote, and then we found its frequency spectrum by using Fourier transform. In Fourier transform, we simply introduce this iota omega term, which is very important, this iota omega term. Then you have to simply solve it. On solving and substituting values, we are left with this thing. As intensity is directly proportional to square of field vector. We know intensity. We often say intensity is directly proportional to amplitude square. Here amplitude means the square of field vector. This whole is the electric field vector, and here we would square it to get the value of intensity. Intensity is proportional to E square. Remember, I am not saying E naught square, which is simply the amplitude. But here we are concerned with the whole field in itself. We are going to write the E T form. We need the complete electric field associated with the oscillator. Now we have to square the value that we have obtained. On squaring, what do we get? E naught upon 2 pi whole square, 1 upon this quantity whole square. I omega omega naught. Before we had E omega omega naught, now we are writing the intensity. So intensity would take its place. This becomes E naught upon 2 pi whole square into magnitude of, we have to find the magnitude of this quantity. 1 is fine. We can further mention it as E naught upon 2 pi whole square, 1 upon magnitude of this gamma by 2 minus iota omega minus omega naught whole square. We want the magnitude of this quantity gamma by 2 minus iota omega minus omega naught whole square. Only squaring will not help, because here we have complex number. This is not a normal number, this is a complex number. When we have to find the magnitude of anything, since intensity is square of electric field vector, we need the whole magnitude. Only squaring will not give us the magnitude, because iota term will always be there. So to find out the magnitude, we have to do one more step extra. How we will do? Let's see. So just remember, this is the term that we have to solve. First we will square it, and then we will find its magnitude. Let's write down. Our term was gamma by 2 minus iota omega minus omega naught whole square. So on squaring we get, this is a minus b whole square, so it's a square. A square plus b square minus 2ab is the expression. So gamma square by 4 plus iota omega minus omega naught whole square minus 2 into gamma by 2 into iota omega minus omega naught. This get cancelled. Now what is iota square? This is minus 1. We get gamma square by 4 minus omega naught whole square minus iota gamma omega minus omega naught. Now we have to find the magnitude. Since I told you that simply squaring a complex number will not help, because even after we square a complex number, we will still get iota, which is an imaginary number. And to find the magnitude, we want to get rid of this imaginary part. So we have to do one step extra, which is to find the magnitude. So now we are going to find the magnitude of this expression. So magnitude will be, how do we write the magnitude? Let me give you the expression first. Magnitude of a plus iota b is under root a square plus b square. This is the magnitude formula for any complex number. So all we have to do is first square the components, both the real and imaginary components, and then we have to square root it. So here this part is the real and this is the imaginary. So let's square it. So gamma square by 4 minus omega naught whole square. Since this is the real part and we have to square it, plus now we have to take the imaginary part. You can also bring minus sign, that won't create much difference because square of minus is again a positive number. So just square it. Now let's open the brackets and expand it. So this would become gamma 4. Let me just write it properly. Square root. Now this is gamma square by 4. So this will become gamma 4 upon 16. This is again a minus b whole square. So a square plus b square minus 2ab. So a square plus omega minus omega naught whole square. No need to open this, as this is again a minus b whole square, but we need not to open this. And then minus 2ab. So this would be 2 into gamma square upon 4 into omega minus omega naught whole square. Further from here, what do we get? Plus minus minus, or minus squared is again a positive number. So this is gamma square omega minus omega naught whole square. Just keep on solving. This gives us 2. So we have gamma 4 upon 16 plus omega minus omega naught whole square minus gamma square by 2 omega minus omega naught whole square and plus gamma square omega minus omega naught whole square. Here you can see this is gamma square omega minus omega naught whole square and this is gamma square by 2 omega minus omega naught whole square. So gamma square and omega minus omega naught whole square is common and we are left with here 1. This is 1 and 2, this quantity, and here this is 1 by 2 into. So 1 minus 1 by 2 will give us 1 by 2. So gamma 4 by 16 plus omega minus omega naught whole square plus gamma square by 2 omega minus omega naught whole square. Now you can see here that this again forms an expansion for a plus b whole square. What is that? This is a square plus b square plus 2ab. So I can combine it again as a plus b whole square. Just check this. Gamma square by 4 plus omega minus omega naught whole square square. If we will open this term, we will again get this expression. This is whole square and then we have a square root. So if we bring this outside the square root, we are left with gamma square by 4 plus omega minus omega naught square. And this is the actual magnitude. We stopped here. This is the part and now we have to write this value that we have just found. And what is that value? Gamma square by 4 plus omega minus omega naught whole square. I'm going to substitute this value here. Again, I have I omega omega naught. I already had E naught upon 2 pi whole square. E naught upon 2 pi whole square, 1 upon magnitude of this term. So 1 upon, and what is that magnitude? This is the magnitude that we have obtained. So gamma square by 4 plus omega minus omega naught whole square. Also, as the frequency distribution depends on intensity distribution, we can write intensity based frequency distribution. Again, we started with E T, then we found the frequency spectrum corresponding to it by E omega omega naught. Then we found the intensity, which is I omega omega naught. Now again, frequency distribution depends on intensity distribution. They go side by side. So frequency distribution is the main that we need, which is given by G omega omega naught is equal to, it depends on intensity distribution. We are going to write here K upon this whole term as it is. Omega minus omega naught whole square plus gamma square by 4. K is a constant. If you remember, this G omega omega naught is the line shape plot. This is the thing, this is the function, this is also called line shape function, which actually gives the shape to our peak, to the line peak, to the spectrum that we obtain. This is the function. The value of this function decides the shape. This is the important one. We are going to use this. I also told that this function has to satisfy a normalization condition, which is minus infinity to plus infinity G omega omega naught d omega, again because this is integral, is equal to 1. So this is the probability that if omega naught is the natural angular frequency of the photons which are being emitted, then omega would be the changed frequency, and all the range of photons, all the photons that would be emitted having frequencies in the range omega naught minus d omega to omega naught plus d omega. Everything will lie in between. Omega naught is the central one, and this omega basically determines two different extreme values. Here we have, that's the broadened line that we obtain. This is omega naught. Now we know this would be omega naught plus d omega. This would be omega naught minus d omega. All the photons that will be emitted, they will be emitted having frequencies between these two ranges. Between these two values, they represent omega. And in the end, we will find the two values of omega. What would be omega naught minus d omega and what would be omega naught plus d omega. This is the main aim of this derivation. G omega omega naught should follow this normalization condition always, and it depends on intensity distribution. So we have found the expression. Now we are going to substitute. When we substitute, what do we get? We get minus infinity to plus infinity, and now this G omega omega naught would be K upon this term, this quantity omega minus omega naught whole square plus gamma square by 4 d omega. If we take gamma square by 4 constant, what can happen? K is a constant, we can bring it outside the integral, no problem with that. Here we can write d omega. Now I'm going to, let's take LCM first, or we just simply take this thing common. So let's take this common. This becomes, this quantity would be omega minus omega naught whole square into 4 by gamma square and plus 1. So I have taken gamma square by 4 common in the denominator. What would happen now? This becomes k gamma square by 4. I can bring it outside because this is damping factor, which is a constant quantity, and 4 again is a number. I can bring it outside, and on bringing it outside, this becomes k upon gamma square by 4 minus infinity to plus infinity d omega 4 upon gamma square omega minus omega naught whole square plus 1. Also, we have to denote this equation. We have to give this equation a number. So let this equation be equation 1. We are solving and we will keep on solving. This is gamma square by 4 in the denominator. This becomes 4k by gamma square and the same quantity inside. This is d omega upon 4 upon gamma square omega minus omega naught whole square plus 1. This quantity again we have a well-defined value for this. What is that? We have a well-defined formula which says that whenever we get something which looks like dx upon x square plus 1, then this is equal to tan inverse x. Here, that's okay. The omega, we are getting omega here. Nothing in the numerator except the differential term. Yes, nothing in the numerator. And then in the denominator, there should be 1 plus the term involving the main variable with respect to which we are integrating. So again here we have 1 plus this whole expression. So yes, we can use this formula here. And if we substitute this formula, we get 4k upon gamma square as it is. Now, I'm going to write down the value, but not the limits. So here I'm going to use bars. See, remember, all the symbol, all the character that we use, they have their own meaning. Since I'm putting the solved value here. If we solve this integral, we would get something like this, tan inverse of the quantity. So here I'm putting the solved value, but I'm not putting the limits. So that's why I'm going to use bar. So bar would state as something like this. This would be tan inverse. Inverse of what? This thing. And this is x square. This quantity is x square. And I need x. So tan inverse x would be what? That would be 2 by gamma omega minus omega naught. Totally fine. 2 2s are 4, gamma square, omega minus omega naught whole square. If we square it, we will get this back. And again, if there is a number always, then that would come in the denominator. This is a rule of integration. We always have this thing, this 2 by gamma, because this is the variable. But if there is any constant quantity, any number that we often call component, that always comes in the denominator. And then we are going to put the limits as such, because we have not put the limits. Now is the time to put the limit. Or before putting limits, let's take this 2 by gamma outside. That would be better. So 4a by gamma square, and this is in the denominator. So when it will come out, it will become gamma by 2. And here again tan inverse 2 by gamma omega minus omega naught. This is minus infinity to plus infinity. Gamma get cancelled. 2 2 is 4. This becomes 2k by gamma tan inverse 2 by gamma omega minus omega naught minus infinity to plus infinity. Now is the time to substitute the limits. Remember, if we substitute the limit, we are going to use square brackets. We are going to substitute for omega. Always remember, we are integrating with respect to omega. So whatever limits we would put, that would be only for omega. Omega naught is a constant quantity. We will not touch it. So this becomes even 2 by gamma is a constant quantity. So tan inverse, find 2 by gamma. This is basically what? Infinity minus omega naught. And then minus tan inverse 2 by gamma minus infinity minus omega naught. Though I'm just writing this particular expression, this step, only to show you what is happening. However, you need not to write this thing because this looks absurd. Anything, if you have infinity and you are subtracting anything, that would not give you any particular number. In fact, it would still be an infinity. Similarly, if you have something as minus infinity, you are again subtracting something, any constant quantity from it, it will not result in anything else. It would be infinity. So I have mentioned this step only to show you what is happening. So anything added to infinity, anything subtracted to infinity, anything multiplied to infinity stays infinity. So this is going to be simply infinity. So I'm just writing here that this is 2k by gamma tan inverse 2 by gamma. Fine, now this is infinity. All these steps I'm just writing down to explain to you. You need not to mention these steps. Minus tan inverse 2 by gamma and say this is minus infinity. Further, anything multiplied by infinity is again infinity. So 2k by gamma tan inverse infinity minus tan inverse minus infinity. Remember, now we have to substitute what is the actual value here, what should come here. If you have remember the tables of trigonometric ratios sine theta, cos theta and tan theta, you must have learned the values for tan 0 degree, tan 30 degree, tan means tangent 45 degree, then tan 60 degree, and then tan 90 degree. If you have learned those values, you must have remembered that for tan 90 degree, whenever we have tan 90 degree, that is not defined. And anything which is not defined, we denote it by infinity. So tan pi by 2 is infinity. So if tan inverse we are saying, because if you take this inverse, if you take the inverse, see if you take tan here, what do we get? Tan inverse infinity pi by 2. Tan pi by 2 is infinity, and if you take tan here, because ultimately tan would go in the denominator, we always cross multiply, right? So if tan comes in the denominator, we would mention it as tan inverse. So tan inverse infinity is pi by 2. And similarly, tan inverse minus infinity is minus pi by 2. So this thing is pi by 2. Should I write? Just hold on. This quantity is pi by 2 and this quantity is minus pi by 2. How? Again, we have a formula. Whenever you have to solve physics derivations, just remember you should know all the basic rules and formulae of differentiation, integration, and trigonometry. This is very important. Algebra, trigonometry, this is very important if you want to do the derivations in physics, because physics use mathematics as its tool. We have one more formula which says tan inverse of minus x is tan minus of tan inverse x. If tan inverse is of any negative quantity, then that would be minus of tan inverse of that quantity. So here we have tan inverse of minus infinity. So tan inverse of minus infinity means minus of tan inverse infinity. And what is tan inverse infinity? Pi by 2. So we get minus pi by 2. So this quantity becomes minus pi by 2. So ultimately, we are having 2k by gamma pi by 2 minus pi by 2. So this becomes plus pi by 2. Finally, we can write down our this quantity k upon, we started with this. This is now 2k by gamma pi by 2 plus pi by 2, which is 2k by gamma into pi, simply 2k pi by gamma. We are left with this thing, and now we have to see what was this term equals to. We were here, we use this condition that g omega omega naught d omega is 1. This is the normalization condition. And we started with this thing. We put g omega omega naught d omega as this quantity. Now we have solved it. Basically, the solution that we have obtained is equal to 1 since we are solving a normalization condition. We are here. Now this is the formula. We can write now. This implies 2k pi by gamma is equal to 1, which further implies k is equal to gamma upon 2 pi. If we substitute this thing in g omega omega naught, our first equation. Now substitute in equation 1. This is our equation 1. We know the value of k. We are going to substitute for k now, because the rest of the quantity will be as it is. Substituting in 1 gives us j omega omega naught is equal to k. Value of k is gamma upon 2 pi upon this quantity, omega minus omega naught whole square plus gamma square by 4. Let's denote this as equation 2. This would give us the shape of the line plot, also called line shape function. So the line shape of such a distribution is known as Lorentz. As mentioned earlier, that homogeneous broadening mechanism give us Lorentzian distributions. So the line shape of such a distribution is known as Lorentz line shape. We have found g omega omega naught, the value. Now we are interested in the maximum value of g omega omega naught. As we know that this is the function which gives the shape to our line, shape to our plot. We know the plot would go maximum and then it would be like this for any particular frequency, say, and then there is the intensity. We are interested in knowing the maximum value. G omega omega naught is maximum when omega is equal to omega naught. Obviously, we can see that the maximum photons emitted give us this line, give us the peak, which corresponds to the omega naught, the central frequency, or here the natural angular frequency. So this function, the line shape, this would be maximum. This maximum I max would be obtained when we are here, when the photons are having frequency omega naught. So that means when our omega is equal to omega naught, in that case our g omega omega naught will be maximum. So we can substitute omega is equal to omega naught to find g omega omega naught maximum is equal to gamma upon 2 pi, since this is the value of k, gamma upon 2 pi upon, when omega is equal to omega naught, this term would be 0. We are left with gamma square by 4. This means gamma upon 2 pi into 4 upon gamma square, which gives us 2 upon pi gamma. This is the value of this function at natural angular frequency. If omega 1 is frequency corresponding to half intensity, let's say that omega 1 is the frequency for half intensity. Here you can see this is the maximum intensity, corresponding to which we have the function g omega omega naught max. This is something at this omega naught. This is fixed. Let's say omega 1 is the frequency corresponding to half intensity. So this is the maximum intensity. So at half intensity, let the frequency be omega 1. This is what we mean here. Then our this line shape function would also be half. If this is the height for g omega naught maximum, then at half the maximum height, this would also be half. This would be half. We can write here, in that case, we would have g omega naught max by 2 is equal to, what is g omega naught max? That is 2 upon gamma pi. Then that would become 2 upon pi gamma by 2. That is 1 upon pi gamma is 1 upon pi gamma is equal to the actual value, this value. This is the value here. So we have to use this value again. The main purpose being, we are just finding g omega naught maximum when the peak is the highest height, highest length. You just say the highest peak, and then the value when this is half. When it is half, g omega naught becomes 1 upon pi gamma, further equal to the value itself, which is this given, the underlined blue box. So I'm going to write this value again. But for omega is equal to omega 1. Now remember, whatever I am doing here now is for omega equal to omega 1, because we have assumed here that omega 1 is the frequency corresponding to half intensity. Half intensity. So this thing, omega 1 minus omega naught whole square. This is the main point. Everything is same. The only difference being here, we have actually given a value to omega. We were talking of that, yes, there are different frequencies. So now we have considered that frequency where intensity is half of the maximum. Now you can see both these quantities are for g omega naught. We know g omega naught is this value also here in the blue box, and we also know now that g omega naught also is this thing when the frequency is omega 1. So if we are dealing with omega 1, we can equate these two quantities because both are for g omega naught. So if we do that on equating them, what do we get? We are going to cross multiply. On cross multiplying, we get omega 1 minus omega naught whole square plus gamma square by 4 is equal to this thing. This is gamma upon 2 pi into pi gamma. That means omega 1 minus omega naught whole square plus gamma square by 4 is equal to gamma square by 2. Further, omega 1 minus omega naught whole square is equal to gamma square by 2. This would go here. So minus gamma square by 4. On taking the LCM, we get 2 gamma square minus gamma square, which is gamma square by 4. Now this is a squared quantity. Squared quantity. So if we have to take the square root, then what would happen? Then this would be plus minus gamma by 2. Always, whenever we take the square root, we always mention plus and minus terms. Why? Because square of positive number is also a positive number and square of negative number is also a positive. That's why we have to mention both the terms. Why these both values? Because square of positive number, that is square of positive number is also positive and square of negative number is also positive. That's why when we take the square root, we mention both because the quantity could be either positive or negative, because on squaring we get positive. This is positive. Now we are about to get the value for omega 1. What would be omega 1 now? Omega 1 is omega naught plus minus gamma by 2. Obviously this is giving us two values. So we say that we have got two frequencies. Now you can see here, I'm talking of the frequency omega 1 when intensity is half of the maximum value. So when we are talking of this thing, when intensity is half, then obviously we are getting two values. We are getting two frequencies here. So now omega 1 is referring to both these values. And what would be those two values? Let's write down. These two values becomes, so we can mention this as, so this implies we get, that is omega 1 dash, one value let be omega 1 dash, which is omega naught plus gamma by 2, and other one we can write omega 1 double dash, which is omega naught minus gamma by 2. Obviously you can see one of the frequency would be to the left of the omega naught and other frequency would be to the right of the omega naught. One to the left of the omega naught, that means lesser than omega naught, and one would be to the right of omega naught, that means greater than omega naught. So this was our main thing. In this way we can obtain the values for any amount of frequencies. Whatever extra frequencies are there except the central frequency, we can find those values. Here we are discussing in terms of angular frequencies and not linear frequencies. Here we have got two values for the frequencies. Line width now would become line width. What is so this is line width. We are saying the intensity is half. For both these values of omega 1, we are getting this width here, this broadening. So we will mention it. Line width becomes delta omega naught is equal to omega 1 dash minus omega 1 double. That means we can subtract these two values simply. If we have to find the difference, we have to subtract these two values. All we have to do is just subtract these two values. So omega naught plus gamma by 2 minus omega naught minus gamma by 2, which is omega naught plus gamma by 2 minus omega naught plus gamma by 2. This is 2 gamma by 2 or simply gamma. Thus we can mention our g omega omega naught, that means a line shape function, in terms of line width. What would it be? Again, let me tell you what was g omega omega naught. This is the formula for g omega omega naught, that is gamma upon 2 pi upon this whole value. So remember now what is gamma. We have to substitute for gamma. So from equation 2, what do we get? G omega omega naught becomes, because gamma is delta omega naught, so that becomes delta omega naught by 2 pi upon omega minus omega naught whole square plus delta omega naught square by 4. Further, what we can do? We can take this quantity common. So delta omega naught upon 2 pi. I'm going to take delta omega naught square by 4 as common. Delta omega naught square by 4. This becomes omega minus omega naught square into 4 upon delta omega naught square plus 1. which further becomes delta omega naught by 2 pi. This is in the denominator. So that would be 4 upon delta omega naught square, and this I will write as 1 plus 4 omega minus omega naught square upon delta omega naught square. Here this delta omega naught square get cancelled, and here 2 is here. We have 2 upon pi delta omega naught into 1 upon this quantity I can write as square of. So this is 1 plus 2 omega minus omega naught upon delta omega naught whole square. Clear? This is the actual value of g omega omega naught. This is the actual value of g omega omega naught in terms of the line width. This would give us Lorentzian distribution. So graphically, this Lorentz line shape we can show as this graph. Let me this y-axis is our g omega omega naught, which is the function, line shape function. We are drawing this or getting this curve with respect to the frequency. As we know, natural broadening is what? That in spite of the central frequencies, in spite of the photons having natural angular frequency omega, we will get some other photons as well. We would get photons having some different frequencies as well. This, the peak, would be for the natural angular frequency, or we used to say it as central frequency. This is g omega omega naught maximum. And what was g omega omega naught maximum? That was 2 upon pi gamma. So I'm going to mention here 2 upon pi gamma. And then the thing we did, we found omega 1. That is for some particular frequency we have found the two different values. And that frequency omega 1 is the frequency at half of the maximum intensity. That means this is the maximum intensity. So at half of the maximum intensity, we have omega 1. Okay. But what is the value of g omega omega naught at half of the maximum intensity? Let's see. This is the value of g omega omega naught maximum at half of the maximum intensity. That is for omega 1. This is the value. So let's show it here. So this is the value 1 upon pi gamma. Once again, 1 upon pi gamma. Now we know we are getting two frequencies here. One frequency would be bit greater than omega naught, another one would be lesser. Both are the frequencies of half of the maximum intensity. That means omega 1. Both are omega 1. But now as we have solved, we have got two values of omega 1. One is omega naught plus gamma by 2 and another one is omega naught minus gamma by 2. So let's show them here. So this one is lesser. So this is omega naught minus gamma by 2 and this one is omega naught plus gamma by 2. So this is the intensity variation for different frequency of emission. Similarly, we can find out for many other. We can find all other frequencies. So all we have to take care is the height of the beam. First we find g omega omega naught maximum, that is for the maximum height, and then for all the heights we can find the value of g, and also we can, like here, we can find all those different frequencies. Similarly, whatever height, here this one is half of the maximum intensity, then you can do 1/3, you can do 3/4. In that case we will be getting all sort of frequencies, all the frequencies we will be getting. Just make sure they would be symmetrically placed on both sides of omega naught. Always the values that we will obtain, they would be symmetrically placed on either sides of the central frequency or the natural angular frequency. So in the previous lecture we explained natural broadening on the basis of quantum theory, that is on the basis of Heisenberg's uncertainty principle. We can obtain the graph, whatever the value that we have found for g omega omega naught, we have found it in terms of line width. So we can obtain the distribution, and remember this natural broadening is the case of homogeneous broadening. So we will get Lorentzian distribution. Lorentzian distribution means we have longer tails. We can draw the graph here. We can show the intensity variation for different frequencies. So this is our omega and this is the g omega omega naught, which is our line shape function. Now you know the peak that we obtain is for the central frequency, which is here the natural angular frequency omega naught. So for this natural angular frequency or the central frequency, we are going to get the peak. That means the intensity is going to be maximum. What was our maximum value for intensity, highest frequency, highest intensity? So that is omega omega naught max. This was the thing. This represents g omega omega naught maximum. So what was the maximum value? Let's see. This was the maximum value, 2 upon pi gamma for g omega omega naught maximum. That is the peak. So here we can write 2 by pi gamma. This corresponds to omega naught because we found this value when we put omega is equal to omega naught. And now the next one. The next was for frequency omega 1, which is corresponding to half intensity. That means half of maximum intensity. In that case, we had g omega omega naught maximum by 2, half of this value. And this value is 1 upon pi gamma. So just write down this value. We can write it here. So let's see, this is the half of the intensity. So this is 1 by pi gamma. Now this corresponds to omega 1. Now we know that omega 1 gives us two values. One is this value and another one is this value. Here we can see we are getting two frequencies. That means half of the intensity would be for these frequencies. Both represent omega 1, but one of the frequencies is lesser, it's lower than omega naught, and another one is greater than omega naught. Here, one is omega naught plus gamma by 2, other one is omega naught minus gamma by 2. So we can mention here, this is omega naught minus gamma by 2 and this is omega naught plus gamma by 2. Thus, at half of the maximum intensity, these two frequencies will be involved. Similarly, we can find the frequencies for any intensity. Could be this was half of the maximum intensity, we can find for 1/3, for 3/4 and so on of the maximum intensity. In that way, we would be getting two values of frequencies. And remember that all these frequencies, they would be like here, this would give us some other value. They would be symmetrically placed on either side of this omega naught. You can see whatever frequency you obtain, one would be higher than omega naught, other would be lower than omega naught. So they would be symmetrically placed on both sides because Lorentzian distribution is almost a symmetrical curve. that we obtain. This is how we can find the frequencies, the value of frequencies for the plot. These are the frequencies which are leading to the broadening of our line. Our line should have been this only, omega naught, but now we know that other frequencies are also emitted, and that is due to Heisenberg's uncertainty principle, which says that delta E dot delta T, that is equal to h upon 2 pi. And we also mention this as h cut, because h upon 2 pi is h cut. Okay, just remember this. So we can explain this whole phenomena on the basis of quantum theory by using Heisenberg's uncertainty principle. So as we know that delta E dot delta T is approximately equal to h cut, and also we know that E is h nu and omega is 2 pi nu. So we can relate energy and angular frequency also, because 2 and pi, these are just constants, h is also Planck constant. This I can write here that my E can be, further, E is h nu and omega is 2 pi nu. So nu becomes omega upon 2 pi. H cut is h upon 2 pi. So if I write here E is equal to h dot, and in place of nu I can substitute this value omega upon 2 pi. Then I can combine h upon 2 pi, which would give me h cut. So I can also write that E is equal to h cut omega naught. Here I am using omega naught because we are dealing with central frequency. This is here central frequency, and corresponding to central frequency we have the natural angular frequency. That's why this we have to use. So if E is h cut omega naught, then this implies that delta E would be h cut delta omega naught, because h is a constant. It's Planck's constant, so we cannot expect this to change ever. So if there is some uncertainty in energy, then that would be simply due to uncertainty in the angular frequency. Now, as the formula states this thing, if I substitute for delta E, it becomes h cut delta omega naught into delta T is equal to h cut, like approximately equal to h cut. H cut gets cancelled and we are left with delta omega naught delta T equal to 1. So delta omega naught is 1 upon delta T. In classical physics, gamma is equal to 1 upon delta T. That means damping factor inversely varies with the time period, or the change in time, or the lifetime. So we can say in classical physics, we don't talk about the uncertainty factor. So we can say that the change in time period, or the way time is going on, forwarding, damping factor would inversely vary with respect to that. As we know, as the time period would increase, whatever wave is there, whatever vibration is there, it would die out. So as time period increases, we say that the amplitude of oscillation, it keeps on reducing. So that's why according to classical physics, we have damping factor is equal to 1 upon delta T, because after all the vibration would die out as the time increases. So you can say that the amplitude is decreasing as time is increasing. So there is an inverse relation. So if according to classical physics we have gamma is equal to 1 upon delta T, so from here we can imply that delta omega naught is equal to gamma. That means what is delta omega naught? This is the line width. So whatever line width is there, that is simply equals to the damping. And the same result we obtained just a moment before. Here you can see, let me just highlight it. Here we obtained on solving delta omega naught is equal to gamma. So that means it's true. On the basis of our quantum mechanics, this is true. On the basis of classical physics, this is true. That means the line width is quite much due to this damping factor, due to the radiations which are being emitted, and we can explain it on the basis of Heisenberg's uncertainty principle also. This relation actually shows that greater the lifetime of an atom in a given state, smaller will be the line spread. So we can say that delta omega naught is equal to 1 by delta t, and delta omega naught is gamma. But from here we conclude that greater the lifetime delta t of an atom in a given state, atom resides between these two energy levels, and greater the lifetime delta t of an atom in a given state, smaller will be the line spread. If the lifetime of this state is more, the line spread in the spectrum would be less, would be small. And if the lifetime of this state is less, then greater would be the spread in the spectrum. So that means if we have metastable states, usually stable states, they are not totally stable, but they are not quite unstable. They are in between, intermediate states, where atom stays for longer times. So metastable states, they have bit higher, bit longer lifetime. So the line will be sharp, because if line spread is small, line is not broadening, that means we will get a sharper line there. And if there are unstable states, then they would be resulting in broader spread. So we can say that, for example, for any unstable upper state, if we have unstable upper state which is having delta t of the order of 10 raised to the minus 8 second, so let me write of the order of, because we never know what is the exact lifetime, and sometime it keeps on changing. So we just approximately equal to this. And in that case, if we have to find the spread, so we know now that delta omega naught is 1 upon delta t. So that would be 1 upon 10 raised to the power minus 8 per second, right? So this is 10 raised to the power 8 second inverse. So what would be the central frequency? Central frequency, now we know this is related to angular frequency with the factor 2 pi. So just substitute the values. 2 pi, this is simply 2 into 3.14, and this is quite a big number. So this would give us 1.6 into 10 raised to the power 7 hertz. Hertz is the SI unit for frequency. So as every level, higher or lower, they have finite lifetime, the uncertainty in the frequency of emitted radiation includes uncertainty in energy and hence frequency of both the levels. So it's all because of lifetime, because here I'm solving everything due to this T. So just say that we started our topic, natural broadening, by saying that inherent line width which arises due to finite lifetime of excited state. So see how important this delta T factor is. Everything depends on this. So due to this uncertainty, or due to finite lifetime, but we don't know how longer would it be or how smaller would it be, there is always uncertainty in the frequency of emitted radiation, and which is further due to the uncertainty in energy and hence the frequency of both the levels, because after all E1 and E2, we say these are E1 and E2. So the lifetime of E2, that depends on this thing omega naught, and it is in turn related to delta nu, which is nothing but E, as E is equal to h nu, right? So all these things are related to energy as well as frequency. So if delta omega 1 and delta omega 2 are frequency width of two levels between which transition takes place. Suppose this is the delta omega 1 and this is the delta omega 2. They are frequency width. So now transition is taking place between E1 and E2, and let this be the frequency width of the two levels. So then the width of line, whatever the line spectrum we are getting, which we denote by delta omega naught, that would be the sum of the frequency width of two levels between which the transition is actually taking place. So here we can further say that delta omega 1 is basically delta E1 by h cut. Just remember that energy E is associated with nu with only h, and E is associated with omega with h cut. And this is further equal to 1 upon delta T1, and delta omega 2 is equal to delta E2 by h cut, which is further equal to delta T2. So now here the frequency width of both the levels are important. It means both states have their own lifetime. The moment it is pending here, after some time it would come down, and the moment it is here, after some time, by getting some energy, it would again go up. So both have their own lifetime, and this transition would keep on happening at some pace depending on the lifetime of two states. So it's not only the upper energy state, in fact the lower energy state is also important. Both of the levels are important between which the transition is taking place. So the width of line would be the sum of both. So this is quite fundamental. This is smaller in magnitude. The natural broadening that comes is smaller in magnitude, but it's observable enough, because this is a natural one, so that's why it is not that dominant. Others overshadow it. Other type of broadening mechanism, they dominate this type of broadening. So the magnitude of this broadening is small, but it is there. So this is always our G omega. You can write omega naught as well. And this is our omega. This is the Lorentz plot. And then whatever spread is there, this is the delta omega naught, the line spread, and which is further the sum of delta omega 1 plus delta omega 2. So this is all about natural broadening, proving that how much the lifetime of excited states, or even both the states, is important. The states between which transition is taking place, the lifetime of those states are really important, because that factor accounts for this kind of broadening in our spectrum, which is natural broadening. Thank you for joining me, and in the upcoming lectures we will continue with other broadening mechanisms. Thank you so much.